Hi class, I just wanted to talk a little bit about airflow patterns and air pressure. I know it can get a little bit confusing about air movements in the horizontal direction and then also in the vertical direction, because when we're talking about weather patterns we need to remember that air also moves vertically. So some of the general concepts that we need to make sure we keep in mind are that air is always going to move from high pressure to low pressure, and that warm air is going to rise, cold air is going to sink, and that our movements of air are driven by that pressure gradient, but they're also influenced by the Coriolis effect and some other forces like friction, most importantly, with the Earth's surface. So first let's start off looking at a low pressure system and a high pressure system here. So remember I said that warm air rises and cold air sinks. Let's think about where would we expect to find these. If we have rising air, that means we've probably got warm temperatures here. So, for example, this happens at the equator, at the Intertropical Convergence Zone, the ITCZ. We have warm air that rises. And so then let's look at over here on the right side and see what's going on here. We have falling air. We have a high pressure at the surface, and falling air is cold air that's sinking. So, for example, this happens at the poles where we have cold air that sinks. So if we have rising air, we have a low pressure at the surface. If we have descending air, sinking air, we have high pressure at the surface. In our low pressure system, we have air that's converging and rising, and in our high pressure, we have the sinking air that diverges at the surface. So our low pressure system at the surface, with surface convergence, rising air, then we have divergence aloft. So what happens is that rising air is going to pile up at the surface, and it actually creates a high pressure system up here. And then you have divergence aloft, but surface convergence here. Now in our high system at the surface, where we have subsiding air, we have divergence at the surface, but we have convergence aloft. And then remember we have the Coriolis effect, which in the northern hemisphere is going to cause things to move to the right. It's going to cause air to curve to the right as it's moving. Our low pressure at the surface flows counterclockwise, and our high pressure at the surface flows clockwise. And that's in the northern hemisphere. If we were in the southern hemisphere, these rotational patterns would be opposite. So our low pressure counterclockwise flow in the northern hemisphere is what we call cyclonic flow. Our high pressure clockwise flow at the surface is what we call anticyclonic flow. So let's look at some air pressure changes and how that affects winds and pressure patterns. So this example is the sea breeze example. So we have the ocean here and the land here, and we have the air pressure decreasing as we go up in elevation. And we have the same temperature over the ocean as over the land, so our pressure isobars are flat right now. But once the sun rises and heats the land up more quickly than the ocean, remember the specific heat of water means that it's going to take longer to change the temperature of the ocean. It takes a lot more heat energy to change the temperature of the ocean. So the land heats up faster. Warm air is less dense, so that air expands. And what happens is those isobars spread out. And so notice at the same elevation, we're actually at a higher pressure here than over here. And so air moves from high pressure to low pressure. And as the warm air expands, we have a high pressure system aloft that pushes the air to the low pressure system aloft over the ocean. And we set up the circulation patterns, and we have this cycle of flow. And this is what we call the sea breeze. That's air that moves from the ocean to the land in the afternoon after it's been hot. So just let's think a little bit more about this warm air being less dense, and why is it that it sets up that pressure gradient? Well, imagine our column of warmer air, and those air molecules are spread out more. And so the point at which we're at, say 500 millibars, is higher in elevation than it is in a column of colder air. And so if this column of warm air was next to this column of colder air at the same elevation, the colder air is at a lower pressure than the same elevation in the column of warmer air, right? Because air pressure decreases as we go up in elevation. So our air is going to want to flow from this higher pressure point in the warm air column to the lower pressure point in the cold air column. At the surface, you might be experiencing lower pressure as that air is rising in that warm air column. Another way to think about it in this example, we've got the same elevation in a warm air column and in a cold air column. And you can think of it as in this cold air column, there's actually less air above you because that air it's more dense and so it's squished. It's squished down closer to the Earth's surface. And in this warm air column, it's more spread out. And so at the same elevation, there's more air above you, and so therefore more pressure. And so therefore aloft, you have a higher pressure, and here in the cold air column aloft you have a low air pressure. So back to our sea breeze example, here's the cycle that we've set up. The cycle that we've set up. So here's our warm air at higher pressure. In this example, we're more than 996 millibars. At the same elevation in the colder air, we're less than 992 millibars. So that air is going to move from high pressure to low pressure. And here now it's colder, so it's going to sink, and movement of air from high pressure to low pressure. And then at night, now the sea is warmer because it takes longer for the water to cool off. The air over the sea is warmer than the air over the land. And so that air is going to rise. We're going to have a high pressure here. The air is going to get pushed from high to low. It's going to cool and sink. And now we have a high pressure pushing the air to the low pressure area here.